Dear participants, we are very pleased to see you on our school dedicated to digital electronics and digital design. Could you please mark in chat, is everything okay? Video, audio, just plus or something like that. Anybody?
If I can hear you and see you, then everything is okay, I think.
Okay. Well, okay. Before we start our program, I'd like to ask our director of Kiev Academic University, academician Alexander Kardyuk, to say a few words. Please.
Thank you, Sasha. Just very few words. Actually, I welcome all participants in this school. Actually, this is one of the last school which we organize this spring. And it is just presented as other schools. We in KAU, we want to support hot topics, especially in physics and other our directions. It is physics, biology, and mathematics, and now it is actually I think although it's not my profile, digital electronics, but I understand that it is a very important age of the research where electronics and experiment meets, and it is very important now. And this importance will be could be illustrated the best, I think, the people from CERN, which is from a Large Hadron Collider, and therefore it is my pleasure to welcome the first speaker. It is Alessandro Caratelli. Approximately a year ago, he gave a talk, and you can find it on our YouTube channel. Very interesting talk about his work, and now I guess he will give more introductory or more educational talk, lecture. And Alexandra, I could say that he completed his master studies in Pisa University and his PhD in EPFL. Lausanne, the very known one of the two most known universities in Switzerland. And he is now a digital design engineer in CERN, and is currently responsible for the CERN ASIC support service. So ASIC, it is application-specific integrated circuit, which is a chip customized for particular use rather than intended for general purpose use. And Alessandra participated in design of multiple ASICs for a number of experiments at Large Hadron Collider. I think he will mention it. And he is also involved in the development of radiation-tolerant solutions based on future detector for electronics, for future electronics, for future detectors. And I remember he talked about this. So welcome, Alexander. Thank you for readiness to give these lectures, and looking forward for your lecture. The floor is yours.
Thank you very much, Alexander. Thanks for the introduction. Perhaps I can start to share the screen if
Have you succeeded, or I should stop it? Okay.
Perfect. Can you see my slides?
Yes.
Thank you very much for the introduction. So today I will discuss about some digital concept for design. Most of these concepts actually apply both for ASICs, but also for FPGAs and for other types of digital design. Uh, I will explain this later during the presentation. So let me introduce myself, but you already introduced me. So my name is Alessandro Caratelli, and I work at CERN as a digital IC design staff engineer. And I'm part of this microelectronics section, which is part of the experimental department of CERN. So just let me say a couple of words of CERN. CERN is basically a research facility, mostly related to energy physics, but we also do research in some other fields. This is located close to Geneva on the French-Swiss border. You can see a picture of Geneva. And in this image, you can see basically the scale of the Large Hadron Collider. This is basically a facility, an accelerator, where are located several experiments, in particular four main experiments, but in general, CERN, there are also other types. And this is an example, for instance, of microelectronics or ASICs that we develop for this type of experiments. In this corner, you can see a photo of the CMS detector, which is one of the four experiments on the Large Hadron Collider. It's very big. You can see here in proportion to a person that is in the center of it. And there is the place where these chips that, for instance, I was working on are located. So basically, these chips are assembled in a module. This module then is assembled in this big cylinder to form a sort of a big camera, but for particle and so on. And this will be installed in next 2 years within the central part of this experiment. This is just to give an example of the type of electronics that can be done in energy physics environment. But microelectronics or in general digital design, also analog design, um, it's in many things. It's not just in this environment. So microelectronics plays a very important role in shaping the modern technology and driving the innovation across various fields. It has revolutionized the way we live and work and interact with the world. You have electronics, in particular digital electronics, a bit everywhere around you. And these impacts are in many fields, like from healthcare, communication, computing, research, customer electronics, and many other fields. Basically, I'm starting with a slow introduction before to go actually into the design flow. But let me just mention, probably you already know this, but all the microelectronics on the current world at the moment, let's say, is mostly based on a particular device, what we call the transistor, which is the basic component of nowadays microelectronics design. Without entering into the physics, and I think you will have actually a lecture that will go more into the details of this object, but what this object does as a macro effect is that when you apply a voltage to the gate, so to the top part there, it creates an electric field that controls the flow of current between 2 points, between what we call source and drain. And generally, you have two different types of this object. What we call N-channel MOS, where when you apply a positive voltage, basically it attracts electrons in the channel, forming a conductive path. And the opposite one, the what we call the P-channel MOS, is where when you apply a voltage, instead create a depletion region, which basically blocks the flow of current between this device. And now here you have an example of three different type of devices on different, let's say, manufacturing technologies, like a bus MOSFET up to the FinFET, which is used more in more recent process, but the concept is very similar at the end. And here you can see actually a photo of this object on the microscope for a 20 nanometer process. And basically, when you hear talking about like Intel is releasing the new processor in a 7 nanometer technology, or when you hear, I don't know, NVIDIA is using 5 nanometer, basically what you refer to is like the size of the length of the gate of the device. So the minimum, the smallest feature that can be manufactured in that manufacturing process. It's not exactly like this in the more modern processes, but more or less that's the concept. And then basically during the last years, an important role took what we call technology scaling. So basically the reduction of this dimension, the minimum size that can be manufactured. And by reducing the size of this transistor, it brings also several advantages and also some disadvantages. But like you can increase the performance, mostly for digital designs, higher integration density, improve power efficiency, increase the functionalities or the quantity of object that you can have on a chip. Like if you think about 40 years ago, maybe in a chip of a few millimeters, you had like few tens of transistors, and nowadays you can talk about billions of transistors in a chip, which means more functionalities as well. And also, this allows to reduce basically the cost per device, even if increasing the fixed cost. We will see this a bit later. For analog performance, it a bit depends on the type of design. Before actually to go more in the details on the how the design works and the process, I want to put there some few concepts. By the way, feel free to interrupt me in any moment if you have questions. So let's firstly divide what is analog and what is digital electronics. So analog electronics is essential interacting with the real world because all the real world phenomena such as sound waves, temperature, voltage levels are all continuous signals. So analog electronics is the part of electronics that take care of reading the sensor, control actuators, measure physical quantities, represent and process continuous signals like amplification, filtering, modulation for communications, and so on. The digital electronics instead, digital electronics, the signals are represented by quantizing them into discrete levels or states. So the digital electronics is the part that take care of analyzing and manipulating the information, implementing algorithm, control systems, arithmetic operations, logical functions, but also is taking care of taking decisions with state machines and algorithm, and can provide the basis, so the basic circuitry for higher abstraction, so something on which you can run software and also artificial intelligence application and so on. They're both important. So an electronic systems always require both because at some point you need the digital for doing all these operations, but you will always need to interact with the real world. So every system at the end include both parts. And nowadays these things are more and more mixed than before on the single chip. So let's take this transistor that we saw in the previous slide and we assemble it in this way. Probably you know what this object it is, but okay, let's say an analog designer will say this is an amplifier because if you look at the characteristics, if you change the voltage in input to this object, what you have is that you have an area where, okay, the voltage saturates to the maximum supply voltage or to zero, but you will have in the middle an area where there is a transition between the maximum to the minimum voltage. And let's say if you approximate the central part of this curve to be linear, you can use this object as an amplifier basically, because you can give a simple, a small signal in input here, and this is in output, you will get the same signal, but with the larger amplitude. A digital designer instead will say, no, this is an inverter actually, because if you digital designer will want to use it this in his stable states on the where the output voltage is the ground or the supply voltages, and we'll call them 0 and 1. And this object will create a logic function which is called inversion. So a 0 became a 1 and a 1 became a 0. And like this, basically, we see that out of this transistor, you can build also logic functionalities. Now, I will not go more in the details of the analog, but I will focus more on the digital world, on the digital side of the electronics. But in the same way as we build this inverter, assembling this MOSFET in different topologies, you create some other type of logic function. Like for instance, in this case, we create a NOR logic function, or in this case, we create an AND logic function. And here you have, let's say, an image of how this looks in the layout. So basically, in the set of layers that you use to actually fabricate this on the ASIC. And we will go to this a bit later. But then basically we saw that with this object, we can create different typologic functions. And now these basic logic cells can be assembled in something a bit more complex, in some more complex blocks and even libraries. Like for instance, here assembling in this way, I created a latch or assembling these digital cells in the other way. You can create an adder or a multiplexer and much more things. Generally, when you do design, at least in ASICs, you have what we call standard cell libraries. So libraries that include a lot of these elements already pre-designed and characterized. And generally, the standard cell libraries include all the basic functionalities like AND, OR, NOR, and so on, inverters, buffers, also flip-flops, latches, multiplexer, but also arithmetic function, shift registers, clock and timing cells, as well power gating cells, voltage regulator, and many other cells to form a sort of a library. Now, using this basic object, for instance, what you can do, you can create even more complex blocks. Like here you have an example of a counter or a floating point unit. In this case, so an object that is commonly found inside CPUs, which is also at the end built out of these logic elements, which are built out of these transistors. And if you go even further, you can create state machines. State machines are basically type of circuit where the output does not just depends on the input, but depends on the current state in which the machine is to decide the outputs. And the state in the future depends not only from the input, but also from the state in which this circuit was in the previous time. And generally, these are made basically having a feedback loop around a memory element and some logic function. Now, in this case, is a very simple example of a four-state state machine. This can be something more complex. Can become something like a CPU. Like here, you have a block diagram of a very simple 16-bit CPU without stages of pipeline and so on. But this is actually a full CPU, which is still built out of all these elements and so on. So for instance, here you can see that there is a program counter, the register file, the data memory, and so on. So this brings me to basically, before to go to the design process, to actually classify the digital circuitry in different types of topologies. Like for instance, here, as we saw before, the CPU is basically a digital circuit, which is particular because allow you to program it. So it's a particular state machine, which basically you have in the memory a set of instruction, and by fetching this instruction, you do a sequence of operation. And the instruction that you put in the memory come from your software. So it's a particular type of digital circuit which is programmable. The GPU in the same way, FPGA instead, I will go more in details in the next slide. And the ASICs are what we call custom integrated circuits. So in this case, is are application-specific integrated circuits. So basically, circuits which are designed for actually targeting one single specific application, but trying to optimize everything for that specific application. So the application-specific integrated circuits is a type of chips designed for a specific application or functionality, different from a general purpose chip like a processor or an FPGA. So the ASICs are designed to meet the specification and the requirement for that application, offering optimized performance and functionalities. Also integrate multiple functions and components into a single chip, and very often integrate both analog and digital blocks that cooperate together. ASICs offer high volume of production and can offer significant cost saving compared to other solutions when you are producing a lot of these objects. And they offer great flexibility since you have a full control on basically everything because you're not basically programming or reconfiguring a design, but you have a full control on every parameter. And in some cases, it's the only possibility to particular requirement. Like for instance, the reason why I'm working on ASICs instead of using, I don't know, FPGAs or processor is because I'm doing the type of electronics that is going within the central part of the detector. And not, because outside of the detector, we mostly use a lot of FPGAs, but in the central part of the detector, we have very high radiation levels. And in this case, commercial electronics that you can buy will not be able to survive. So we need to design custom ASICs, taking into account the reliability in the long term due to the radiation effects. And for this reason, it's necessary to go for ASICs. In some cases, so is the only possibility due to particular requirements. But designing an ASIC is a bit like to have a whiteboard in front. You have a lot of flexibility. You can basically do everything. You're not bounded to certain topologies, but with it, it also come a bit higher complexity. And this is like an application specific IC, so an ASIC production flow, let's say. You start from the design, sorry. You start from the design, both in the analog and digital world. We will go more in the details of the process of designing after. And at some point, you get a GDS file. So basically, a representation of all the layers that are needed for manufacturing this object. Then means that you will need to send this to a production facility, which we call foundry. So companies that produce these chips based on the files that you give them, and they will produce the chips on these discs, which are these wafers of silicon. After that, the chips are diced, so cutted, all the single chips are extracted, and then required to be bonded, packaged eventually, and then integrated into the system. So basically, you see already that from the moment you finish the design to the moment that you have your chip in the application, it takes time, it takes a month. Differently from in the case of an FPGA, where you can just reprogram it on the fly. We finish your design, you reprogram it, and you have your system working. So, depend on many factors. The design of a digital system can rely on instead of configurable or programmable ASICs, ICs. So, instead of manufacturing the design circuit for a specific application, the digital designer can utilize certain type of integrated circuits with particular architecture that allow him or her to configure it or program it to perform the task required by the specific application. And in this category follow CPUs, GPUs, and FPGA. So the designer in this case is not designing is designing the circuit, but in this case, the designer of the programmable or configurable IC often produce the chips in large quantities, allowing a reasonable cost per piece. And then the digital designer, which is using these objects for making his system, does not need to send the object to production because this is already ready. He's basically configuring it to do the specific application. So, for instance, a CPLD or an FPGA is a flexible collection of logic elements and IP blocks that can be configured directly in the field. This in the picture you have an example. I mean, this does not represent all the type of FPGAs, but is to explain the concept. Generally, you have like some cells which are quite configurable and can offer a wide range of logic functionalities, and all of these are replicated in a large array, and the interconnection matrix in the middle allow to connect the input and output of these cells in order to form the circuit. So basically, when when you with your firmware after you do your design, you are configuring the FPGA. What you're doing is basically you are connecting the points. You're connecting the circuit, connecting these points in the matrix in order to create your circuit within the FPGA. Differently from a CPU, where instead you have a set of instructions, so there you have a software running. Um, so different type of FPGAs and also different generation work in slightly different ways. The logic functionalities are there, are different, and so on. But the basic concept is that one. And generally, this connection can be done like with fuses or can be done with writing basically the configuration file in an SRAM, and different bits in this configuration file go to open or close a pass gate basically to connect these points together. Recent FPGAs are more complex than this, but this to explain the basic concept. So the advantage of CPLDs and FPGAs that are configurable for specific application, the functionality can be changed after installation, and they offer quite good performance per watt and massively parallel operation because basically you are implementing your circuit, so you can decide to make massively parallel, or I mean, on an FPGA, you can even put, if you design in Verilog or VHDL a CPU and you configure your FPGA with, let's say, the code of the description of a CPU, basically what you obtain is that this object became a CPU, no? So you can configure in various ways, but it's very convenient to use FPGA also for massively parallel operations because you can have different pieces of circuit operating in the same way, in the same time. And they allow also fast time to market compared to ASICs because you don't need of production cycles. And you don't have a fixed production cost as in ASICs. Of course, the cost per unit is higher compared to ASICs, depends on the quantities. And there is a longer complex development time compared to software itself. And also on FPGA, the number of resources that are available are fixed. So when you buy an FPGA with certain number of resources, if you're doing something smaller, you are not using some part of resources that are there. If you're doing something bigger, you may limited about the resources that are available on it. So it's also a question of selecting the right one. And also you have a fixed availability of analog components. Modern FPGAs include embed some analog components or dedicated logics inside. And of course, compared to an ASIC, there is no control over power optimization. The other great category is the software programmable ICs like CPUs and GPUs. I will not go too much into the details, but let's say the CPU are a processor for general purpose application, and they offer a very great versatility and programmability as the GPUs, but the CPUs are optimized for sequential processing, while GPUs are more optimized for parallel execution. On CPUs, you can have higher clock speeds, while on GPU, you have lower clock speed but higher throughput compared to the CPU. And of course, both of them only offer digital processing versus an ASIC where you can mix everything together. CPUs are more suited for control logic, GPUs are less suited for control, are more suited for control and sequential algorithms. And a particular type of CPU that I like a lot, it's like the RISC-V. Because the RISC-V is actually not a CPU. RISC-V is an open source instruction set architecture designed for modern computing devices, offer simplicity, scalability, and versatility. So RISC-V instruction set does not define how the CPU need to be implemented. It just defines the instruction set. So you can and this is open source, so means that then you can also use the same compiler if you develop your own CPU or you take a CPU and you customize it. There is a lot of great RISC-V implementation of CPUs that are open source that one could take, customize it for making meet more target for their application and still be compatible with the instruction set and therefore to the compilers and so on. And it's a modular design. It offers modular and extensible architecture, allowing designer to tailor the processor to the specific application and requirement. Also support multiple standard extension for customizing the processor, like integer, floating point unit, vector, cryptographic instruction, and so on. And RISC-V can be implemented from across a wide range of devices, from the very low power, simple and embedded system CPUs to the high performance and supercomputing and so on, enabling basically with the same instruction set a diverse type of applications from IoT down to edge computing and so on. So in the last year, they became very popular for embedded systems because it's well suited for low power, resource constrained, but also for high performance computing, giving to the scalability, the extensibility, and so on. And they took a large plate in education and research because being an open source and quite simple. It's an ideal platform for teaching computer architecture, conducting research in academia, and also make real projects. In fact, for instance, in the chip I'm working at the moment, it's a pixel detector array, so it's an ASIC for reading out pixels and so on. But on the side of this chip, embedded inside the chip, we also place a RISC-V CPU to do some control operations instead of having custom state machines for that. And then another category is what we call system on a chip. System on a chip means that you're integrating in the same chip different things, basically. You integrate multiple hardware components into a single chip. can be a CPU with FPGAs, like for instance, Xilinx or Altera provide Intel and AMD actually now provide these objects which are FPGAs with embedded inside CPUs and other dedicated hardware resources inside, or can be a system based on a CPU with different hardware accelerators around, or mixing basically multiple functionalities. Like in the case of the chip I'm working on, is a pixel array which is custom for an application, but it also has some configurable and some programmable objects inside. So system on a chip means to put together multiple types of hardware into a single chip. And the advantage is that you achieve better physical footprint, so more functionality in a smaller space with multiple components. You minimize the interconnect lengths, reducing signal routing. You don't need to go out of the chip and back inside another chip. And therefore, you can achieve also very high power efficiency. And the integration enable optimized communication, reducing latency, improve overall system performance, and a cost reduction. Because you saw the process of producing a chip costly, not only from the point of view of production, but also all the phases of assembling and that come after and the logistic. In this case, you can do this for a single object, so because multiple functionality are in the same chip. And also it enable hardware, firmware, software co-design. Just to give you an example, this is the Apple CPU, which was in the iPhone 11, I think. You can see that in the same chip, they included CPUs, GPU, neural network hardware, memories, and other custom hardware, all in the same chip. Of course, I mean, we saw before in the slide of the production phases of producing an ASIC, and you can see that there are several costs involved, like design cost, the verification cost. It's not negligible because verification takes a lot of effort as well, and the production of the mask for the fabrication process. This is the main cost for an ASIC. Then you have also a cost for wafer produced, the packaging and the testing costs, and all the supply chain. When you instead of using custom chips, you use configurable chips like FPGAs. Instead, you have the design cost, of course, that's a fixed cost, and the verification, but you don't have a fixed production cost. You have a variable cost per each device that you buy for the application. So it's obvious that there is a point where these two things meet, and if the number of chips you are producing is above a certain number, it's cheaper to do ASICs. If it's below a certain number, it's more convenient to use configurable chips like FPGAs for doing digital
Alessandro,
signal.
what is the number
Yes.
of components? It's just number of pieces which you produce, which they produce.
Yes, number of pieces that you produce.
Okay.
So like for FPGA, if you need, I don't know, 100, you buy 100 FPGA and you pay for this 100. If you're doing an ASIC, instead, you pay fixed cost of production that um, depends on the process you're using. Can be, I don't know, $100,000 or $10 million, depend on the process. But this cost is fixed and is just for creating these masks for, okay, let's say for lithography and so on. So basically, this object that you need for setting up the production process. And this cost is fixed independently from how many chips you will produce. So if you produce 10 chips, the cost per chip will be very high. If you produce, I don't know, 100,000 chip, you will spread this cost on 100,000 chips. That's a bit the point. And yeah, and so this is like a slide. Okay, don't get scared about this number. They're not real. I found this slide online and they over exaggerate on the numbers on the side. But this picture show basically that for different process nodes, let's say you are going from 65 to 5 nanometer, the cost of production, but also the cost of all the design, verification, and everything else increase sort of exponentially. But the point is that when you design an ASIC, it's not that you always need to go to 5 nanometer or 2 nanometer or to the latest process that is available. You select the process according to the application. Like automotive, all the chips that are in the car are mostly in under 30 nanometer or 65 nanometer. where you can reduce the cost, but also they give the performance that they need. I mean, to go to 5 nanometer is only for very high, if you want really high, very fast circuitry. Like you will do this like for CPUs, like the i7 and so on. But for custom electronics used in a car or used in other objects that you have around, you will not need to go to that. And then for prototyping, this is mostly used by small companies or universities and so on. There is a possibility which we call multi-project wafer. In this case,
Alessandro,
basically, the prototyping.
sorry,
Yes,
sorry. Could you just previous slide? I just didn't understand. Maybe I missed. Just did you say why it's so? Why smaller sizes cost so much more than
because okay,
for design? It's not really clear.
pretty much is the latest. This goes with the time. Let's say no, the 65 nanometer process was released around 15 years ago by the major foundries and so on, and it was much more expensive when it was just released. Now that it became more a stable node, the
Ah,
prices went down in the
it
time.
just because technology developed, yeah, and you put
Yes,
here development of technology.
yes, and then there is also another factor. For very high scaled technologies like below 16, you are going to this FinFET instead of using bulk CMOS technology and so on, which require a larger set of masks for being produced. So, for instance, for the lithography process, you need a larger amount of masks and so on, and this increase also the
Right.
fixed cost. So there are also some. It's not only from the fact that the process is newer, but also there are some, let's say, technical reason why the process is more expensive. But in average, the trend that you see in the market is that the latest process is always much more expensive. And then after some years, once this became more popular, the cost start to reduce and the, the newer process have this higher cost.
Yeah,
So let's say,
it's
generally on this
interesting
5
that
nanometer,
all the components are more expensive. All the components which you shown here, yeah, and production and physical and verification,
yes,
everything is
yeah,
more
okay, this is an image
expensive,
that
more
I found
expensive.
online, but yes, there is some more complexity also in the design and verification. Uh, these also do because, for instance, the set of rules that you have for manufacturing and so on are more complex. So in this case, basically, you need to meet all these rules, and also since the production cost is much higher, sometimes it's convenient to invest more money, which means basically more time of people into verification to be sure that once you send the chip to production, you are, let's say, close to 100% sure that it will work, because otherwise you will lose a lot of money. While, of course, when designing in a cheaper process, you can accept to do multiple prototypes or to send it to production one more time with bug fixes, so perhaps you can spend less time into verification. It's
Yeah, okay,
basically
okay,
higher
okay.
production cost. Makes sense?
Yeah, okay. Thank you. I understand. It's just I just also wanted to close this question about price. That previous question when this price for ASIC and FPGA crossed. So I just wanted to ask which the number to understand what is the number of components it corresponds to this crossing
This
approximately.
is a bit difficult to say
Yeah,
as a number because it
I
depends a
mean,
lot on
100,000, an order of magnitude, order of,
uh, okay, this depends a lot on first of all which technology we are talking about, because of course if you are designing an ASIC in a under 30 nanometer or 250 nanometer, the fixed cost, it's way lower. So you can, I don't know, I know that a full mask set in 65, here you are in the order of 800,000 euros. On 130 or 250, you are in the order of 100,000 euros.
No, I
Here
mean
you
not
are in
in
the order of
euros, not
millions.
in euros, but in numbers of chips, numbers of
I know
chips.
exactly, but just to make this comparison, I need to think like this more or less the cost or the different process, no? So basically here depends on the FPGA that you also want to use. And then FPGAs they exist from the very cheap one to very expensive one. So it depends on the also the type of design, no? If it's a simple object or if it's something we need to include a lot of complex functionality in it. I think it's
Okay,
per
okay, but
project, difficult to
okay,
define.
it's understand that, for example, when you design a new ASIC,
Yeah.
and you order how many identical chips you order, then it's interesting.
In our case, it's in the order of 100,000 chips or
Uh-huh.
200,000 chips.
Uh-huh. So you have a lot of chips to try
This was in the case,
to
for
burn it,
instance,
and so on. Yeah. Okay.
this was in the case of the outer tracker of CMS. Other projects, instead, they have much lower amount of chips, like, I don't know, order of a few hundred.
Mm-hmm.
Still, we need to do ASICs, but there is not, it's really not related to the cost, it's more related to the fact that commercial electronics that you can buy is not radiation tolerant. So the only way to make it radiation tolerant is to make something custom.
Mm-hmm.
So sometimes what forces you to do ASICs is the fact that you need the requirement that nobody offer you on the market.
Okay, thank you.
But there is actually a way to reduce a lot of this cost, which is this MPW. MPW means multi-project wafer, which means that on the same reticle, on the same so on the same mask set, you put multiple designs, and this generally convenient if for numbers below 500, where the mask cost can be shared among multiple designs. And this is generally used either for prototyping, but it's also used for small amounts of production because sharing the cost with other make the technology easier to access, mostly for research and for small companies. And in this case, basically, it makes it accessible for instance, for us for prototyping or for small company for prototyping or even for small amount of production. Because you're spreading the cost between multiple entities that need to agree on using the same process, but it's doable. And also selecting the technology node, as we said before, influence a lot the prices. Also, there exist European programs for sharing the cost for universities and startups, and start to appear also some open PDK low-cost fabrication process like the Skywater, which, for instance, is an 130 nanometer process which allow very cheap prototyping on an open source process, open source design kit, actually. Going now more into the now I want to go a bit more in the details on the process actually of designing for the digital design. These most of the things that I will discuss are valid both for ASICs and FPGAs, but then I will go a bit more in the details of the latest phases of production for an ASIC. So before actually to enter this, one more concept that is probably worth to mention is the difference between full custom design and what we call semi-custom design. Full custom design is when basically the designer has a full control to customize the layout of the circuit for each component. He can draw basically everything. This offers the maximum flexibility because you're actually drawing how the transistor is done, basically. But of course, this is time consuming as not automatized process, not very automatized process. This is generally used for analog design, but also for high-speed communication and power circuit, and as well in digital design, where you have very extreme requirements. That's while generally for digital design, what you do is what we call semi-custom. Basically, utilize pre-designed and pre-verified components, and you assemble them. But this process is much more automatized because you're describing the circuit at an higher level of abstraction, and then the designer can describe the functionalities higher level and use some software tool to generating actually the physical circuit that you're going to produce. And this is suitable for digital design. That's how you do digital design in general, except if you have very extreme requirements. And so before actually to go to the design phase, it's important to understand how the different abstraction that you can have at the level of a digital design. So the same circuitry can be represented at different level of abstraction if you want. So let's start from the architectural level. At architectural level, you describe the overall architecture, the organization of the digital system, the major components, the interfaces, the interaction. And here you have, for instance, a block diagram. You can do this in some dedicated languages like System C and so on, but you're describing the architecture of the system. If you go a bit lower level of abstraction, at this level, you can describe the functionality. TLM stands for transaction level modeling. At this stage, you can describe the functionalities and the behavior of the system, but not the implementation details. So you're focusing on what the system does rather than how it does it. And here you have an example in System C of a simple counter. A lower level of abstraction is what we call register transfer level. Here, basically, you're doing a detailed modeling of the digital system, and you represent the systems in terms of register, data path, control logic. You specify with clock cycle accuracy how the data is transferred and what the logic does, and which operation are performed. And here you have an example of the same counter, but written in Verilog. Basically, this functional and register transfer level is mostly where the digital designer works, because what is below is not something that generally you write by hands, but is more like generated using using a software tool that you instruct what to do, but is generated. So going to the lower level of abstraction, we have this logic level where the circuitry, the digital circuit is represented by logic expressions. Usually this is not written manually, but it's generated by what we call generic synthesis. And these represent the same counter of before, but with logic operation like you see NAND, NOR, wire, and so on, which does the same functionality as what we said before. It's just a lower level of abstraction, and this is mapping directly to this circuitry that you have on the right. If you go even further to the gate level of abstraction, here you represent the digital systems in terms of gates and interconnection, and also including constraints and timing behavioral of the individual gates and flip-flops. And in this case, the netlist is instantiating the actual building blocks that are defined in the standard cell library. So if here I have a logic function NAND or OR, here I will have basically the actual OR cell from the library that implement that functionality. And this, of course, is specific to the manufacturing process that you are selecting, or for the case of the FPGA, okay, it's a bit different. And here you have an example in Verilog as well. The names are used as not real. And then you can go even further, what we call switch level. So where you represent the digital system in terms of individual transistor, so not logical functionality, but transistor, and other components that are associated with a physical model. And here I specify the behavior of the transistor, also in terms of electrical characteristics and switching behavior, because basically here you have a list of devices like resistance, capacitance, transistor, and so on, and each one of them is associated to actually a model that can be used to make an analog simulation out of it. This provides a higher level of detailed view of the hardware implementation. And here you have an example in this language called SPICE. You don't write this manually, you generate it this, but it's good to know it. And then on the lower level, you have the physical abstraction. Here you're representing the physical layout and characteristic of the system, providing actually a complete view of the hardware. It includes all the placement of the cells, the routing information, the metals that connects the cells between each other, and so on. And here we have an example in the DEF format. It's a format to describe the physical abstraction of the circuit. And here you have an example of a visualization of this. So basically, at these different levels, we represented the same simple counter, a different level of abstraction. And then while doing this, I show you several languages that were used to describe this. Generally, I told you that the digital designer mostly work at the RTL level or the functional level, okay, as well at the architectural level. You don't really write the code at a lower level of abstraction. But in fact, for hardware description, the most common languages are Verilog, VHDL, and System Verilog. You can see that Verilog allow you to go very down in abstraction, down to the gate level, lower than VHDL. But VHDL can arrive to a bit higher level of abstraction. You can create things at higher level compared to Verilog. System Verilog is nice because it includes all the Verilog plus an additional set of functionalities which are more abstract on the top, and as well is suited for not only for test bench but for a full verification environment and so on. But of course, you can describe at higher level of abstraction also using um, like languages which come more from the software world, like Chisel or System C, and even C++. And this became more popular in the recent year with the level synthesis. But here you cannot describe the lower abstraction levels. The advantage of these languages is that they allow you to put in the same, to describe hardware and software together. And okay, of course, so programming languages then allow you to describe only software. At the low level abstraction, we have the SPICE language that we mentioned before, and the left def on the low. But mostly the digital designer work in the Verilog, VHDL, System Verilog, which are at the end totally interchangeable languages. I would say that for FPGA, VHDL is a bit more common. For ASICs, Verilog, System Verilog are a bit more common. But you can do everything with all of them. Okay, I don't know. I think um, basically I instead of having two separated presentation, I did the one long presentation. So tell me when you want to break it before to start the second part, since I have basically these two consecutive presentations. Probably here is a right moment to break it and take questions on the first part because before after I will actually enter more than the phases of designing.
Dear participants, do we need 5-minute breaks? Please write in the chat.
Yeah, I
Yes, if you want,
think
we can take 5 minutes break.
it's better, Alessandro, define where you need a break because it's much harder to speak than listen. And
I think this could be
just
a right moment
give time for
to.
questions if listeners, if students have questions, would be nice at this point, right?
Yes, because then I will start for the next topic. So
Okay. Any one has a question?
Yeah, can I have a question?
Yes, please.
sure.
So Alexandro, in your experience, how often as a designer do you really need to go lower than uh, functionalities that covered by system Verilog and VHDL? How often do you need to go to gate level or transistor level? Maybe not to design, but like optimize some things.
Let's say you mostly work at the functional or RTL level. There are some cases where you really want to optimize some circuit, so you want to describe it at, let's say, logic level, just placing actually the standard cells to do some very optimized circuitry. It's a bit more rare. So, for instance, on the project I'm working on, I'm doing this only in for inside the pixel. I really want to optimize the area, so and I'm using some asynchronous state machines, so some particular things. So then I'm writing at a lower level. Otherwise, you generally don't. But it's good to know all the different abstraction levels because these allow you to understand what the process that I will show later does. Because basically, once you write your code, you pass it through synthesis and then through physical implementation and so on. And to understand what the synthesis does, the synthesis basically allow you to go down in this abstraction. Uh, Basically, allow you to create a gate level netlist out of RTL description and you want to extract how the synthesis is done with constraints, but also with some scripts that tell the software that run the synthesis what to do and how to do it. So in this case, eh, it's important to know what this means.
We have a question in the chat. Have you ever had to work with spice? Alessandro, could you answer, please?
Directly spice? No, cioè, I mean, you mostly don't write that. But this, for instance, for analog design, when you draw a schematic, so when you draw a circuit schematic of transistors and so on, this is directly basically matched to a spice netlist if you want.
And
The same level of abstraction. You do graphically in analog design, but it's on that level of abstraction that you do it.
could you say your preferred software in your work?
What do you mean? Language or?
I mean language and software package.
Okay. As a language, I'm using mostly System Verilog. This because I would say VHDL is more common for FPGAs. For ASICs is more common System Verilog. No particular reason. I think it's mostly just historical. You can do ASICs with the VHDL and you can do FPGAs with System Verilog. They're interchangeable, but I'm mostly using System Verilog, just historically. And softwares, I mean, depends. If you work on FPGAs, generally, maybe if you're using
FPGA.
Xilinx, you will use Vivado. If working on ASICs, mostly the tools, the commercial one that are available are from Cadence and from Synopsys or from Mentor Graphics, which Siemens, sorry.
Mhm.
Also, there are different companies decide to use the software tools from different companies.
We find
And
that there is no open source software for FPGA to implement.
they start to exist. Let's say they start to exist open source tools, both for ASICs and for FPGAs. So they exist something like a IOSIS is one of them, which is nice, I would say. It's still not comparable to the commercial ones, in my opinion, but it's getting developed fast. More and more people are starting to use, so it's very interesting actually to look into it now because in the next year can be something really usable even for production. Nowadays, I would say yours is, for instance, works good for a research project, but not for a big production object.
Okay,
But
thank you.
it's evolving.
More questions? Or can you describe open source software and design tools like Open Road, open source PDK, and your experience with them, if you have any?
Yeah, so it's a bit what I was saying. Let's say for open source tools is a bit this, the fact that they're nice, they're evolving quickly. They're still not on the level of the commercial one. Let's say so. But for instance, open source simulators are already great. I would say like Verilator is an open source simulator for very low code. It works very good. Yosis for the synthesis is working, let's say, quite good. For the implementation, is still not at the level of other commercial tools, in my opinion, but it's going in the direction. And then for open source PDKs itself, for the moment, that I'm aware, there is not many of them. There is, for instance, the Skywater that I mentioned before. I mean, it's let's say I see it more suitable for research and university now than for real production. But it's the open source is appearing more in that. While for what concern open source hardware in terms of IP blocks, like blocks in Verilog or in higher level abstraction, like and so on, this is basically in the last year it did. There was a revolution. Now there start to be a lot of open source. Starting from the RISC-V, a lot of open source architectures, implementation of RISC-V processor that you can use, modify, and put inside your own design, and a lot of other IP blocks. Like if you think to the open hardware repository or in general, for instance, for the RISC-V, there is a very nice course that are coming from the Pulp platform from ETH Zurich that now basically they created some course that now became a sort of standard, like the RISC-V became a sort of a Linux, but in the hardware world, for instance. So in the last year, there's been really a revolution in terms of open source.
Okay, maybe we continue.
Yes. Can I come in 1 minute? Just I take a
Sure,
bit of water.
sure.
Hello. So shall I continue on the second part of the presentation?
Yes, please.
Okay, so what we need to start designing, in particular for ASICs? So first of all, we need a lot of informations about the fabrication process itself that we select. So we need what we call technology files, which are process-specific information that define all the characteristics of the semiconductor manufacturing process, including all the available layers, properties, and rules. Then we will need the models for the devices, like describing the electrical behavior that are used to simulate the circuit, and a set of design rules which define the geometric constraints, the layout, and so on, and also libraries, support scripts, PCS, documentation, and much more. All this set of files all together makes what we call the PDK, which is the process design kit. So most of these are provided by the founder itself, but can be customized partially in some things. The design rules, no, but depends. And the designers basically use the design kit to simulate, to draw, to verify the design. The same on FPGA is pretty similar in the sense that when you use an FPGA, you need to select for when you compile your code for which particular FPGA you are implementing your circuit to generate the configuration file. And also there, the software tool behind need to know these informations about for which process, for which FPGA to target the compilation. And then we go actually into the design. So generally, when you do a digital system design, you will start from some ideas and the requirements of what you want to do. And based on that, you most likely will define an architecture that you are going to implement and also get some specifications and some metrics. Then after that, in some cases, you may move to a higher level modeling. Not always necessary, but sometimes it's useful to make a model at higher level. And then you finally go for the hardware description, which in the digital world means hardware description mostly in mm, system Verilog, or VHDL, or even to higher level of abstraction. And in an analog world means to design your schematic of your circuitry. Of course, this needs to be associated to a verification process. So, and I saw that you will have actually a presentation about verification later today or tomorrow, I don't remember. But verification basically here means that you will need to verify that what you describe as hardware is actually matching the specification and the matrix that you place at the beginning. And eventually, if you have a higher level modeling, you can use this as a reference model for your description to match, to see if what you implemented is actually what you wanted to specify from the beginning. And then in the side of the analog, once you do the schematics, you will manually draw a layout, most likely, and you will create a model that can allow you to integrate this block into a digital on top design. While on the digital side, together with the hardware description, you will need to write some additional constraints for the software tools, like constraints in timing, in power, corner definition, and take some technological choices, and so on. And then you move to a process which is called synthesis and physical design, which we will see in next slides. And after that, you basically, your chip it's ready. Now you move to the sign-off checks. Sign-off checks is basically the checks that you do at the end just to be sure that things are good. And finally, you can send the chip to production. Once you receive back the chip, you will need to do some testing and so on. Somebody was asking something? Okay.
No, there was an echo, sorry.
Sorry. So, as you see here, I color the things in different colors. There is a reason for this, because these are actually generally done by different professions which are involved in the design of an ASIC. Like what is in pink here is mostly done by what we call a system architect. This part is more done by the analog designer, and this by the layout engineer, or this by the digital designer, or the physical design engineer in this case. Then there is the verification engineers. Then there is the physical verification engineers. And all of these need to be supported by data tools and infrastructure engineers, and also by the process engineers, the one that handle you all the process side. And of course, also the testing engineers for testing the chips at the end. And maybe this chip will actually go on a larger system. So we need to involve again the system architect, but also the PCB designer engineer, which is the one that is making the boards on which this chip will be placed, and so on and so on. So it's actually a lot of different professions. Now, at CERN, but in general, in research world, we don't have like people so specialized in different functions, but many people, most of us do multiple of these functions. In the companies depends. Some companies really specialize for these, each specialize different people for different functions, different teams. Some other tend are more flexible. So for instance, in some cases, the digital designer is only doing the digital design. In some cases, is also doing synthesis and physical implementation, or and so on. Sometimes the schematic designer in analog and the layout engineer can be the same person, and some other times are not. But these different companies does in different ways. In the research environment, mostly we divided this in the digital designer does also synthesis and physical implementation. The analog designer does everything concerning the analog, and then there is the verification engineers, which actually handle the part of verification. The process for FPGA, it's not different. It's very similar, actually. Also, here you will have ideas and requirement and architecture definition, and you will specify some metrics. And also there you do an hardware description, and you will need to write some timing constraints. You have a bit less choices to take in terms of technology because the hardware you're buying is fixed. And of course, the synthesis and implementation are more automatized compared to the case of the ASICs. Because in this case, you have a fixed hardware and you're not actually placing a route in the cells, but you are connecting an hardware which is pre-designed if you want. And in this case, the FPGA programming it's also fast because you can upload the firmware and it runs, compared to an ASIC where the production phase, it requires to send a file, a GDS file, send it to production, wait a few months, get back the chips, and so on. But conceptually, the two design flows are very similar in the reality. So let's go a bit inside this design flow. Let's start from this high-level modeling, which is not always necessary, but it's useful. So often, before starting the actual design, it can be convenient to create a simplified model of the system. And this allows you to study the architecture and take design choices. And this can be at a high level of abstraction, like a transaction level modeling and so on, and does not need to be clock cycle accurate because it allows you to fast prototyping, you know? So in a standard design flow where you don't have this high level modeling, you will need to explore the architecture. You pass from the specification to the hardware description, verification, matching to the reference model, and so on. Well, in this case, you can actually turn around fast between this model and the specs until the model match the specs, and then try to your hardware implementation try to match to the model. So sometimes it's useful to do this level of abstraction in the middle to model the system before to start designing. And then you go to the actual hardware description. So here you describe the behavior of the digital circuit in terms of control circuit, data transfer, logic operation, and so on. And you describe not only the functionalities to implement, but also how these functionalities are implemented with the clock level accuracy and the structure of the hardware component. And here you use specialized languages like VHDL, System Verilog, and Verilog. And here you have an example of a counter, an example of RTL design, behavioral modeling in System Verilog. After that, if you saw the plot before, okay, sorry, before to go to the synthesis, actually, hardware description sometimes can be done also with different approaches. Like, for instance, the RTL code sometimes can be convenient to write some scripts for generating part or your Verilog or VHDL code. Just to give you a few examples that I use, generate some Python script for generating the interconnects among modules based on a YAML description file. I mean, this is not a standard. It just sometimes it's faster to write a script that write to some part of the Verilog, mostly if it's repetitive, than to actually write the code itself. Or sometimes you can use some tool for generating memory mapped interface and register files which are compatible to a specific protocol out of a system RDL description file, or some script to add some redundancy for making design tolerant to faults. This is something we use a lot at CERN for radiation, mostly for a single event effect tolerance. And another thing is high-level synthesis. High-level synthesis basically means to use higher level languages like to describe the hardware functionalities. This is something that became popular in the last years, in particular for machine learning dedicated hardware. And here common languages that are used are System C or Chisel, but even others. And there are specialized high-level synthesis compiler, which basically out of this description allow you to generate the Verilog or VHDL code. The advantage is that the design is faster and you can use existing software libraries from C++. The disadvantage is that you don't have control on the architectural design choices since you specify what you want, but not exactly how you want it. And usually it's less optimized results in performance, but it's for sure interesting. So it depends on the application. Sometimes it's useful, sometimes less. Depends also on in the same chip. You may do different things that sometimes you want to optimize down to the single register, the single gate, or the single standard cell, and some other times instead you can do usage of a level synthesis. And then you move to the next step. So if you see this description, after the hardware description, we go to what we call synthesis. The synthesis is the process basically of transforming the high-level description into your actual digital circuit basically in the optimized gate level netlist, so to the lower level of abstraction. Generally, you start from the design description files, so your code, the constraints, and also information about the power. some more things. And also you need the standard cell library. Standard cell library we saw before, it was like a library including all the basic building blocks. So the synthesis is an automated process and you use dedicated software tools. Like for FPGA, this process is mostly automatic. So the designer can act on the constraints and so on, and then on the settings. For ASIC, you have much more flexibility. So it's a bit less automatized. You basically end up writing some scripts, a lot of scripts in generally in Tcl or other languages that basically instruct the software tools on how to do it and what to do it. But the concept is the same. So basically what we see here is that at the level of generic synthesis, what we are doing, we are passing from the RTL level hardware description, that level of abstraction, to the logic level hardware of description. So the level of abstraction where we have logic functionalities, which maps directly to basically this circuitry below. And I'm using the same example of the counter that we saw before. Then, okay, we have some optimization stages and so on, where the tools will handle how to optimize the logic, to reuse blocks, uh, remove what is not really needed, and add what is needed. I will not go too much in detail of the optimization, but the next important step is the technology mapping. Here is where we are moving from the logic level of abstraction to the gate level hardware description. So basically, we are mapping these basic functionalities to basically standard cells from the library that you give in input to the tools. And these cells, they have actually their own circuitry and layout. So you're actually in placing the real cells that you're going to do. So basically, you have a netlist of cells defining the standard cell library at this stage. So basically, we talk a lot about, I mentioned a lot standard cell library. What does it mean? Okay, the design library in general, you have three categories. Most likely, you have libraries of your custom blocks, can be analog blocks, can be digital blocks that you design before or somebody else designed, and so on, that you want to place inside your chip. You will need a library of I/O cell. So I/O cell are basically the cells that are used for driving the signals on and off the chips. And the library usually include input receivers, output drivers, and ESD protections. And these cells are typically fixed in height and typically also in width. And then you will have what we call a standard cell library. So the core, so basically a library which include all the functionalities like arithmetic functions, and or not, clock gating, power gating cells, and other functions. Generally, the standard cell libraries have a fixed height and a variable width. The reason for this is because most of the approach we use for placing these cells into the chip is to draw some rows and then placing inside this row these cells. So if they're all the same height, basically you can place them one next to each other and then you just route on top. And this simplify the process basically. These cells generally are designed to be extremely compact and to provide a good performance and low area. I will not go too much in the details about this, but if you have questions, feel free to ask me. I can go more in the details. The design libraries, either if it's standard cell or if it's your blocks, can be a digital or analog blocks that you design and you want to use inside your new chip, need several views, several description of the object. Then you need a functional model, which is required by the simulation. So a model of the functionality of the P block.
Yeah,
Yeah.
I'm sorry, I have a question. On the previous slide, what do you mean by height? The number of transistors in a block, or
No, the
like
physical dimension. So
the physical dimension? Or
yes, on this
on circle?
direction.
Ah,
Maybe I can show
okay.
you
Uh,
if I have some other image.
mm,
Okay, but probably it's
yes.
visible in this one. You see that here I have a lot of rows in this chip. Generally, what
Uh,
you do is that these cells, I don't know if you see my mouse.
mhm, yeah. We can see your mouse. Yes. This is this an FPGA
Yeah.
that is shown here, or is this an ASIC?
This is an ASIC.
Okay.
It's an example for an ASIC. On an FPGA, this you don't have, in the meaning that
Yeah.
in the FPGA, it's already done, this job. So somebody already did the physical implementation of the FPGA, and you are basically connecting logic elements to create the circuitry, but it's already drawn. In this case, in an ASIC, you have basically, you can do anything. It's like if you have a whiteboard where you can start to draw from scratch. You don't have, let's say, dots that you can connect. So all the part of the digital design and writing the Verilog of VHDL code is identical. The part of synthesis and the implementation is a bit different because in this case you need to place the physical cells that will be produced.
Mhm.
I don't know if it's clear.
Yeah, and so that it's just I didn't think that like the circuits can be multi-layer in physical sense. I thought that just all the transistors are just placed one after the other, not like they can be stacked vertically.
Uh, yeah, no, so actually you need multiple layers because yeah, the transistors are one next to another, but you need multiple layers to fabricate the transistor, and then you have
Oh,
multiple layers of routing, one on top of the other,
ah, okay. So
for
the
connecting
height
the blocks together.
the height is in relation to the number of routes. Yes, and
No, in this case, basically, just looking the chip from the front, approach that is used is basically to basically place these cells one next to each other, but to make them all the same size, so that when you assemble, you place them easily next to each other, so they have the same sides in one direction and a different size in the other, just to make them next to each other, and facilitate the routing and so on. Because basically, each of these cell will have a stripe of power on top and a stripe of ground on the bottom. So if you can abut them next to each other, you can create these rows of power which distribute powers between them and so on. But I think this will be more clear in the next. We'll have a slide about floor planning,
okay.
and will be more clear there.
Let's continue. Thank you.
Yeah. So about the digital libraries, generally you need several views to represent these libraries. And these views include, generally you want to have a functional model. So generally simulation require a functional model of the cell of the epi block. And this can be in Verilog, VHDL, or for analog blocks can be in Verilog A and so on. Then you will need, of course, some documentation because it's always good to have some documentation. Even as an engineer, I never like to write the documentation, but the documentation is important to explain how the block work and what it does and how to use it. And you will need maybe some verification views. So often for analog blocks, this they will come with the test bench or some test vector for the verification scripts. Or often the digital blocks come with a test bench or an UVC. UVC is basically what we call a UVM verification component. So it's a piece of software, it's an object that can be easily integrated into higher level, system level verification environment. But basically, it's an object that allows you to be integrated in a more complex verification that you're doing about the chip and have a model of this IP block. This is generally not for the standard cells, but for objects that you have in a library of complex blocks. Like because we saw that we can integrate also other digital design that we design that we did before inside a chip, and like this create a hierarchical design basically. And then these are what we call the design views. The netlist view basically represents the block as a list of the basic devices, so transistor, resistor, capacitors, and so on, and the interconnection between them. Then on the physical side, you most likely need to have for this IP block what we call a layout view. A layout view is the full set of physical information, including all the fabrication layers for the devices and so on. Basically, how the block will look like, the reality. And common format are def or GDSI, which is a database of the fabrication layers. But in the reality, to integrate this block in your design, you don't really need all this information. You need a very small subset of them. So that's what we call abstract view. There's a minimal required physical information about the cell. Basically, want to know the physical dimensions, the shape, the location of where the inputs and output are placed, and the routing blockages. So basically, where you should not route on top because there is the physical block that you're going to include inside. And a common format for this is what we call LEF. I'm giving you a lot of names. You don't need to remember all of them, but as a reference is something that you can find. So the LEF file, or say, open also the abstract view, basically allow you to give you this abstract physical view of the block.
Alessandro, there is a
And
question.
then, yes.
Chat. I can
In the
read to
chat.
you if you don't see a chat. Am I rightly understood that
Sorry, no.
previously connection between these doors should be known? But what should an engineer do if he bought a good board, but connection between doors is not known?
No, I didn't really understand. Sorry.
I think it's probably connected to the previous slide where you're
Please.
talking. Luca, maybe you could just unmute and ask.
Yeah, sure. So
Oh.
I heard that you called the kind of legs in this chip kind of doors with a connection. And what should I do, for example, if I bought a board for my small project and manually the seller is not giving me any type of any type of instruction about connection between these doors? How can I know it? All I can do is just trying to catch a signal between these doors, or there is something better or maybe
Like
easier?
outside of the chip, you mean
Yes.
to communicate to the chip or what?
Yeah, communication between processor and the chip on the board.
Generally, these need to be documented. So when somebody produces an ASIC or produce a different type of chip and so on, need to document which pin is doing what. If the chip is a package, you will have probably in the datasheet of the package, what is routed to each pin and so on, and also
Okay,
the electrical characteristics of the drivers or the receiver that you have on the chip
but
itself.
it's still possible to do it experimentally, yeah, to understand to which door is connected
Yes.
to pin. Okay, I see. Thank you.
Yes, it depends a lot on the type of chip, so it's difficult to say that in general, no? But yeah.
Let's continue, please.
Yeah. Sorry, I didn't see the chat, but in case, feel free to just ask me directly questions. Then, okay, another important view, it's the timing and noise models for the library. Timing and noise models basically are used for static timing analysis to ensure timing closure that meet the performance requirements. So basically, what you want to characterize about this cell or this block is the timing constraint to interface to the block and set up for setup and all checks and timing checks between the inputs, but also timing characteristics on the blocks as the delay of propagation of the signals from the input to the output, the timing arcs, and so on, and also the noise propagation of the cells and so on. These are usually given in a format called the liberty, which is a .lib file. Okay, just these are format, a language. And the most common format variants are these NLDM, ECSM, and CCS. I will not go more into the details. If you're interested, I can explain you. Static timing analysis is the process of ensuring that the design meets the timing requirements and can operate reliably. So timing constraints are generally defined, some timing constraints, when you do the design, you need to write some timing constraints. which define the timing relationship and guide the analysis process, okay? And this you will see in the next slide. What is it? But timing models of the standard cell also define propagation delays, noise margins, which are their margins in input and output for setup and hold of the single cell, and the input capacitance, and so on. So the static timing analysis basically allow to calculate the arrival times and the required time for each flip-flops or for each element, let's say, accounting for the propagation delays and all the clock signals. Basically allow you to calculate all the timing arcs from one, for instance, from one memory element like a flip-flop to the next one, all the possible combination of timing arcs, all the propagation delay, taking these values from the library, from the timing library of the standard cell, or also taking into account more advanced, also parasitics effect, capacitance resistor after extraction, and so on. But calculate all this path and then check if these match the margins of setup and hold that are fixed for that cell. And this is common between ASICs and FPGAs, it's the same. The static timing analysis take into account process variation, variation on chip with on-chip variations, take into account uncertainty, also parasitic capacitance, glitch propagation, slew margins. I just put here this as a reference. If you're interested, I can explain you more in the details, but we don't have time to go too much in the details of that. What is important there is basically the main types of checks that you want to see is like what we call setup and hold timing checks. So basically to check that the minimum time that the data needs to be stable before each clock edge, and the minimum time the data needs to be stable after the clock edge. Violating setup timing checks basically means that the design will not be able to operate at that frequency, but still, if you run it at lower frequency, you gain margin. So basically, the design will operate at lower frequency. Not exactly. In some cases, race conditions on is not really like that. But let's say if you have a static synchronous signal with a single clock, that's how it works actually. If you run at lower frequency, it works. While all timing, no, if you violate all timing, so this is much more critical, can bring to actual functional failures. So this cannot be fixed by reducing the operating frequencies. And here several techniques are used to fix all the issues. But basically, static timing analysis, what is doing is checking several things, and the most important there are setup and hold timing checks. To do so, the designer, once writing the code, also need to write the timing constraints, which means defining the timing requirement, a relationship within the digital designs, relationship inside the digital design. So you need to specify the behavior of the signals and the clock to ensure proper synchronization. And then the timing constraints can help identify and prevent timing violations such as setup and hold violations, which can lead to functional errors or timing failures. And here you have an example of SDC constraints. This is a format for writing constraints. You can see here basically I'm defining a clock on which pin, which frequency it has, which is its waveform, the load capacitance, the max fan out, for instance, the max transition, the clock uncertainty, the input and output delay, all this information that the synthesizer need to know for doing the synthesis, and also the static timing analysis need for evaluating the timing. And this is the same in ASICs and in FPGAs. And then we move to, at this point, we are at the end of the synthesis. As we saw before, after the synthesis comes the physical design. The physical design. So the physical implementation basically is the phase where the synthesized netlist is now transformed into the physical layout, basically to generate what you send for production, for fabrication. And here the main steps are the floor planning, the placement, the clock tree synthesis, the routing, optimization, and the sign-off. And the main milestones are, of course, time enclosure, verify that the functionalities are met, that the power requirements are met, and verify that the design is manufacturable. There are a lot of smaller steps, but these are, let's say, the main steps. Also, in this case, you start from a gate level netlist, you have your constraints, comes out of the synthesis most likely, your power intent will describe say, power intent. So, and you will need to have the timing models for the libraries, for all the standard cells or other blocks. In this case, you need also the physical informations and the power information and the PDK, what we saw before, this design kit, which include a lot of other things. Like in this case, we need extraction rules and so on, which are part of the PDK. And then the fourth stage is what we call floor planning. Floor planning basically is you are defining how your chip physically will look like. So you're partitioning the chip, placing the major components to meet the design constraints like area, power, or signal integrity. You define the location of the key elements. Like here in this case, this is a real chip that I'm showing here. And here in this case, I placed some memories in this part, some analog blocks here on top. Here are some other digital blocks. Here I have some DRAM, some SRAMs and so on. Here I have some IO pads, and all the gray, all the rest in the middle is digital standard cell, which are very small and spread around. But basically, it means to define the physical layout of the chip. And and then also you will need to power your planning to plan your power. So basically to the power grid distribution, how the power is distributed around the chip, defining which part of the design is going different power domains. Because for instance, on the same chip, you can have some areas working at different voltages, or you can have some areas that have a voltage which is dynamically controlled to save power, like in modern CPUs, or something when you don't use something, you can actually power it off. So you need to also draw how the power is distributed and which blocks is using which power domain. And then you move to the next step, the placement. This is mostly automatized. Still, you can take decisions. But okay, here basically you can see what you were asking before, what I was meaning by rows and height of the cells. Somebody was asking this question before. In the placement, of the standard cell, what you're doing is that you're placing all the cells within your layout from the physical point of view. And here you can see basically all these cells. Generally, the approach that you use is like to draw some rows because all the cells are the same, have the same size in one of the dimensions. And then you place basically in this way, you spread them around. This process is mostly automatized and is taking into consideration also the timing. So it's trying to put together cells that need to communicate in order to optimize the routing, optimize the timing, and so on. But this is mostly automatized. You have a lot of settings, so that's why basically you provide some scripts for doing this, but it's software automatized. In FPGA, instead, generally this is you don't need to take care of it. It's like part of the process. It's a totally automatic. So this I think should reply also to your previous question.
Yeah, Mikhailo
Then,
says thank you.
okay. Then after the placement, the next step is what we call the routing. So you want to connect these blocks together. So the routing is the process of establishing the interconnection between the components, and it involves, okay, global routing, detailed routing, and assignment of via, insertion, optimization, and so on. Generally, global routing means to, okay, I will not go too much into details because I'm going to be a bit out of time. But basically, okay, the routing is the process of connecting all these cells in order to actually create your circuitry. And here in different colors, what you see is different layers. Because generally, when you manufacture a chip, you have multiple layers of routing, one on top of the other. Here we are looking the chip from the top. But if you look from the side, you can imagine each color, it's one layer, one above the other. And you will need some things like power analysis, evaluating reliability, like power analysis. The objective is to evaluate and optimize the power consumption to meet the design goals, because sometimes you want to do something low power, or sometimes you want to be aware about how much power, which is the power consumption of your chip. Also, another important thing is the airdrop. So, okay, if you have basically a resistance, a resistive path between 2 points due to the power distribution, and if you have a certain amount of current passing through this resistive path, means that you have a voltage drop. And this means that your cells does not see the voltage levels that you were expecting, but see a bit lower voltage level. This is important to evaluate it because this can affect, of course, the performance of the circuitry. Imagine a digital cell, if you reduce the voltage, it will be slower. Simple as that. And okay, a bit more complex of that, but this will affect the timing, increase the delays, degrade the performance, and so on. And then also another thing is the electromigration. So the movement of metal atoms due to the electron flow, leading to material degradation. So you want generally to guarantee that the chip will work for a certain amount of years. So you will do some electromigration analysis to see how much year the chip will be able to survive, taking into account this effect. Or maybe you will route your lines a bit larger in order to use the electromigration effect. And then you need to do a physical verification. So ensure the correctness of the manufacturability of the layout before fabrication. The foundry, so the one that is producing your chip, is giving a set of rules, which are called the DRC rules. These rules basically, if you check all these rules, if all these rules pass, means that the design can be produced, can be manufactured in this process. So they include like a minimum distance between object, minimum distance of the metals, minimum spacing, minimum width, overlap, and so on. And also density of metal and antenna rules. Density is actually interesting because you will think that why I need to have a minimum density. This is because when you produce metals in a different layers, if, for instance, one layer has a low density in some area and higher in another, on the next level you will have a passivation, a silicon oxide, and the next level of metal, and so on. At some point, you will start to have basically this layer sort of bending, you know? So to avoid this effect, basically you put some dummy pieces of metal in order to make it the layer as flat as possible, and so on. All these manufacturability rules come from what we call ERC deck. And then another thing is the LVS, and the extraction also. In this case, with LVS, what you want to verify is that the layout, so the physical implementation of your chip, actually match your your schematic that you simulated before. So basically, you want to see that the physical implementation of the chip actually does what you described at the beginning, to match the things together and be sure that what you're going to produce is actually what you wanted. And finally, you go to what we call the sign-off checks. Sign-off checks is like all the set of checks that you need to do at the end of a design phase to see that the chip does what is ready to be produced. So it includes behavioral description and RTL description of the design need to match the requirement. And this you do in the verification. So it's mostly the verification engineer which does this. So you need to ensure that the verification reach adequate coverage in terms of code coverage, functional coverage, and also direct tests. And then you want to check in static timing analysis that there is no violation in all process corner, including on chip variation, parasitics, and so on. So at the end, on the let's say with the extraction on the final physical design, you want to check that the chip is manufacturable, so pass the DRC rule. You want to check that the physical design is functionally equivalent to the description. So we use this LVS and also logical equivalence checking, so checking the entries at different points. And then the design pass all the power integrity checks. So power analysis, airdrop, and electromigration that we saw before. And then when you pass all this checklist, you say, fine, now I'm ready to send the chip for prototyping or production. No? And then this is what we call tape out. Tape out is basically this stressful moment in which the archive, the database, including all the fabrication information of your design, which is called GDS, you send it to the fabrication facility, to the foundry. And here you have an example, like this is the ASICs GDS file of a chip. These are real chip that I was doing. Well, it's abstract, and this is actually a photo of the same chip at the microscope, and you can see that actually match. They look the same. And and then after, let's say, a few months, you receive actually this chip, and then you're ready to test it, to package it, to use it, and so on. And congrats, actually now you passed all the design phases of an ASIC. And here I put some photos of some ASICs that we've been designing for energy physics in the last few years, and several others. So yeah, I think it's all from my side. I left here some useful links um, follow this school. It's actually very interesting. You will have a lot of nice materials. I saw the program of the presentation they are going to have today and tomorrow. That seems very interesting. And I left you here also some links about the CERN Ukrainian Remote Summer Student Program. This could be interesting for students. And also Remote Summer Fellowship Program, the RISEP Fellowship Program organized together with KAU. And here you have the link. And actually, I saw there is a Victoria connected, which she's part of this program, and she will work actually with me in the next for 3 months. So thank you for attention, and if you have any questions, I'm happy to reply. Excuse me, I cannot really hear you.
I think it's Victoria talking, and she's happy to introduce her. Victoria, we don't hear you well, but you can type in the chat if you want.
I have a question. What are the languages that are used in like a higher level description during the first stages of development? I forgot.
Yeah, so it's pretty much this. So basically, I mean, on the digital side, this for digital design only.
Yeah, for digital.
The most common language for hardware description are Verilog, VHDL, and System Verilog.
No, yes. So Chisel and System C probably. For like the first you showed the diagram of like
yeah, for high level modeling.
The process and yes, so yeah, for high level modeling. So System C is mostly used. Yes.
Yeah, I mean, in the reality, I mean, an high-level modeling can be done with pretty much any languages. Many people just use the software languages to make a modeling. So C++ is also common. Let's say System C is actually a library for C++. It's not really a language, if you want. It's more like a library on top of C++, which give you some constructs for hardware description. That's why System C is a nice language for this. It's basically C++ with some features for hardware description. It's a library on top. So that's why it became popular for that purpose.
Okay, thank you.
There is a question from Victoria. How intensively machine learning is being integrated into ASIC design lately?
It's something that it's becoming more and more popular. It's something that becoming more and more popular. Let's say it's a growing field, both in terms of integrating machine learning inside the chips. So basically, to make chips that provide hardware architecture for running machine learning on top. For instance, it became popular to basically develop some hardware accelerators dedicated, for instance, for vector operations or TensorFlow as hardware accelerator for to be associated with a processor and so on. But basically, the processor is delegating certain operation to this hardware accelerator, or like dedicated chips for this, say chips that implement neural network functionalities and so on, which enable at the end machine learning. And as well, on the other side, this is also used in the design, on the opposite side, let's say, even design tools that you use for designing ASICs start to integrate machine learning functionalities to help you to automatize certain functionalities, certain decisions in the design phase, and so on. So this is something growing very fast. I would say that for the design we do at CERN, it's more common on the FPGA side in the back end of the experiment, not so much in the ASICs that are in the center of experiment. And the reason is mostly because of power requirements that we have there. But I could expect that the next generation of ASICs we are going to do for the detectors for the experiments, they will probably start to integrate some machine learning functionalities inside.
Adding to this question, is examples of realizations when FPGA is used as actually the program, included in the algorithm of machine learning algorithm when its structure changes during learning?
That's a very nice approach. In fact, I mean, that's actually something that FPGA is allow to do because FPGA for their nature, yeah, they have a fixed architecture below, but the circuitry that you do on top, you can customize. So basically, you can change the circuitry that you're implementing for the functionalities that you need. So FPGA is something that allow to do that, in fact. And I think this is a field in which people are moving. All these things are in fact very interesting and are quite relatively new, let's say. It's few years that start to appear, these things that you mentioned. And I believe they will grow a lot in the future.
Okay. I have a few general questions maybe, but I would wait if more specific questions, students have more specific questions, so maybe.
Can I ask maybe off topic and stupid question? Could you please clarify if we buy a CPU, ordinary CPU for computer, cooling system connects to backside of the buffer or some layer add on the top and then it's produced packed to be connected to cooling system.
So to the top or to the bottom? Okay, these are basically different ways of connecting. Perhaps if I can draw somewhere, we'll explain you this. Let me see if I can have a sort of whiteboard.
There should be a whiteboard in the share options, share screen options.
Where?
When you start to share screen, you can choose one of windows or you can choose a whiteboard.
Ah, okay. Nice.
Yeah, so you can see it.
Yeah.
Okay, imagine that this is the chip that you're doing or that you're buying and so on. There are, let's say, three typical ways. Okay, then can have multiple other possibilities, but let's say common typical ways of making this interconnection. One way is basically that you place all the I/O cells, so drivers, receivers, all around the chip, blah blah blah, all around. Here you have your core functionalities, and then you use what we call wire bonding. So you basically have some wires which goes from here to here at the level of the chip. Another thing is what we call bump bonding. This is what we call, oops. Okay, fine. This is what we call bump bonding. you place on the top of the chip some bolts, basically. And these bolts allow you to connect the chip to the package or directly to the PCB, depends, and so on. If you look at this from the side, basically, this is your chip. This is where you have your transistors and so on. Here you have all the routing layers and so on. And then basically on the top level metal, oops, on the top level metal, you will have these bonds. And another approach, instead of what we call TSVs, in this case, you do the opposite. If here you have all the metal layers, here this is your silicon substrate, you create what we call a TSV, through silicon bias. So basically you have an opening, oops, here, an etching from the lower M1 metal layer, and then you have the bolts on the bottom. And then these things can be mixed. Huh? I hope this reply your question.
Yeah, I think so. So Sasha.
Yeah, thank you. Partially, at least.
Right, these are just basically the three main approaches for connecting a chip.
Okay, one of general question just for understanding, I don't know, physical trends. So the ratio, let's say, ratio of speed, for example, if we compare ASIC to FPGA to just fast processor realization of some algorithm. So what are this ratio, the order of magnitude? It's interesting, and also how do they change? How do they evolve with scaling, with decreasing of the size of the elements?
Let's start from the point that basically an FPGA or a processor are basically a particular integrated circuit. When you do an ASIC, you can do an FPGA or a processor. So basically, there are just basically a particular design that is defined for some type of application. No? So when you do an ASIC, you optimize to the maximum to what you want to do with it. So you do basically a chip which is really optimized for that application. When you use a CPU, for instance, CPU generally give you quite high clock frequencies because, and these they quite high clock frequencies, but they can be very efficient for running an algorithm which is sequential on the top. An FPGA basically, again, there you're defining your hardware, so you can optimize. It can be like if you have something which is highly parallel computational, or not even parallel, but if you want to have like different functionality running in the same moment, because then an FPGA can be more efficient. Because a GPU, for example, yes, allow you to parallelize, but to do the same task on a lot of things. On an FPGA, you can basically implement different pieces of hardware doing different functionalities, all of them in the same moment. So it depends a lot on the applications. If you're talking about um, clock speed, then okay, that's not really a fair comparison. What you want to see is like the throughput of your application. And of course, if your algorithm is sequential, CPU will be the best. If your algorithm is very parallelizable, probably with FPGAs, you get the best results. On an ASIC, you can do everything customized to the maximum for that application. And inside your ASIC, you can put a CPU or you can put other pieces of logic. So inside ASIC, you have a whiteboard. You can put everything you want inside in the reality. Then it's not anymore application specific, it became just an integrated circuit, but with a lot of different pieces. It's what we call the system on a chip.
So you mean it's hard to say, but I just expected for that when you design ASIC structure, you can should run first this algorithms just in this model on normal CPU, yeah, and you just model this algorithm, and you could measure, or you could understand how which advantage, how much speed increased when you then run them on real ASIC.
Yes. You can kind of
But it
simulate
depends
these and
on
so
the
on.
task. I understand it depends on the task, but actually the order of magnitude, but it is difficult to change, to say. Okay, I
Yeah.
understand.
Let's say if you run, let's say, let's imagine we are running something sequential. Generally, maybe on FPGAs, you can run with clock frequencies on the order of hundreds of megahertz. CPUs can go to gigahertz. On the ASIC as well, you can go to gigahertz clock speeds, depends on where. On ASICs, most likely we'll do some parts running at different frequency.
Okay, and
But it's very task related, so it's
and temperature optimization. Temperature optimization, as far as I understand it, it's something which is built, yes, it is automatically. This software makes it automatically. Is it correct, or
yeah, basically
optimization
for
of
the
the
power.
structure for temperature?
Yes, for this basically for what concern all the power related things. I mean, all these steps that I show you are mostly automatized. Still, you need to write the scripts to tell these softwares what to do and how to do it, because you have a wide range of possibilities on how to do things, you know? So you basically extract the tools with some scripts. But in general, yes, this process is automatized. Basically, what here you want to do is this, for instance, for the airdrop analysis, you will need initially to extract the parasitics, so basically evaluate capacitance and resistance for each net in the design, how much each cell is drawing as power consumption. This the software will do it. Huh? How much each cell is drawing according to the voltage that is operating at, to the, for instance, even the waveform of the current of the voltage that receiving inputs, it changes the waveform of the current that is drawing, and this will affect, for instance, the current distribution will have maybe a voltage drop, and this will affect the speed of the cell itself. So it's a lot of calculation that a software does it for you. You don't do it. You extract how the software need to do this calculation, and here you have a representation, for instance, of the voltage drop.
But is it considered as a hard problem? No, since it seems for me that this is one of the places where machine learning algorithm could be helpful.
This is actually absolutely this is one of the main problems. That's one of the main reason why sometimes design they don't work, because these things have not been analyzed properly. And absolutely, there machine learning can help a lot. Yes.
And also, I was wondering when you order when you make the design order and get back from manufacturer this ASIC in real chips, do you check them? How do you check them? I mean, do you microscopically, thermally? Which kind of checks are you doing, or you don't?
Mostly the check that you do is like testing the chip, like functional checks. Okay, this is actually a photo on the microscope, just with a normal microscope, not even in the lab, just done on my desk. This photo on the right, of the chip, not of the transistor, of course.
So it's not some serious, let's say. Serious, I mean, I know, yeah, that for example on synchrotrons, some time of usage of synchrotrons by companies that produces chips, and they are looking on them and they examine them. So that the question was whether you use some kind of such extensive investigation, or it is done by
Okay. We do extensive testing of the chips, and generally we do for this large scale production, like this for another project that I just finished. Basically, what we did is that, actually for this chip here and this chip here, what we did is basically do what we call wafer probing. So basically, we prepared a testing algorithm on this is running on an FPGA in the reality. And then we have a probe card, which is basically a lot of tiny needles, which goes to touch on top of this wafer even before cutting it. And they touch the pads all around the chip. And touching this pad, they can provide the electrical signal, so they can basically use the chip, you know. And then on the FPGA, we run some testing routine, so like sending test vectors and receiving test vectors. Also for testing the fabrication of the chip, so if the chip works or we need to exclude it, we use an approach which is called scan chain. Scan chain basically means that all the flip-flops of the chip are connected in a long chain of flip-flops, when not when the chip is functional, but only for testing purpose. So you can basically shift inside a test vector, give a pulse of clock, and then shift it outside. And this allows you to test in a few hundreds of milliseconds, basically basically everything on the chip. And generally, this we do from an FPGA.
Very time consuming, right?
Yeah, but in the end, with this approach, it's time consuming to prepare it. But then the probing itself, the wafer prober allow you to step very quickly on top of the wafer. So then it became fast the process itself of testing. But it required to prepare all the tests.
You are cutting then wafer by yourself, right?
No, of course, this we send to some companies to do it.
No, okay.
If you want to have a photo of this, I can share you.
I would just expect that you get from manufacturer already cut it, something like this.
When we do an MPW, so for prototyping this multi-project wafer, which means basically sharing with other people, then yes, we get it already cutted. But for large production, we decided to send directly the wafer to the company that then is assembling these chips on the PCBs, because also this we outsource it to a company at the moment, or often we do with universities instead. In that case, in the case we decided to ask them itself to do this dicing operation to cut the chip, basically.
Okay, thank you, Alessandro. Thank you for the nice lecture. Maybe more questions, Sasha?
Very nice talk. Question maybe later, much more later.
Then I will stop the recording.
Okay.